Anyway, yeah, great to see a few people coming into the session, even though it's not the session that you were probably promised. It's very sad to hear that the speaker couldn't make it, but things happen. So let me quickly introduce myself. This is my LinkedIn picture. Speaking of performance, it performs really well with recruiters in the sense that they don't write me messages anymore, which is great. I live in Zurich, Switzerland. I was born and raised in Germany. And you know what they say about Germans, they don't have any sense of humor. So it's like, how many Germans does it take to change a light bulb? One, because we are very efficient and have no sense of humor. I will probably, this is a very serious picture, so I totally live up to that standard, right? I'm a developer advocate for weapon search at Google in Zurich, but I find that very clunky. So someone else once said, I'm the open web cheerleader. And I'm like, yay, which is probably living up to the expectation. So I'd rather call myself that rather than the developer advocate at Google. So, okay, that's enough about me. I think there's a few more things, like I swim home from work in summer and stuff, but I think that doesn't matter that much. So anyway, let's have a look at web rendering and rendering performance on the web. It's getting technical, but not too technical, because this is like an introduction, and I want to take you on a tour behind the surface and basically explain a bunch of things that normally are not really explained that much. Like, we have probably heard the term hardware accelerated when it comes to performance. We heard we want to have 60 frames per second when we have animations or things going on our website, but what does that actually really truly mean? Okay, let's start with how well, you know what? We're going to wait a little bit. We make people feel a little awkward for, just like taking a lot of time. Because there's plenty of seats available, and everyone's like, ooh, no. I got to pick a seat at the very end of this room. Feel free. There's plenty of seats available here. Don't worry. You can just come down and have a seat. First row. That's like VIP stuff. I'm going to come and shake hands if you wish. Or not, if that's what you wish. I'm flexible. No pressure. All right, so as there's a few last people coming in, I assume last people, I don't know. So, when the browser starts to retrieve the data over the network for a website that we navigated to, it doesn't get an image, unless that is actually an image. But if it's a website, what we are getting is a bunch of markup, which is technically text data, right? So we get a bunch of text. And as that comes in, so we don't have to wait until all this has downloaded. This could be much, much larger if you have looked at the source of any modern web application. It usually is a lot larger. But basically, we don't have to wait for everything of this to appear. Basically, we can start building stuff the moment, or displaying stuff the moment we get a piece of information that we can work with. And the very first thing that the browser does is, whenever it sees that it has an entire element ready, and it understands what it has to do next, then it creates an entry in what is called the DOM tree. So basically, it takes note. It's like, okay, let's have a look at this. So there's an HTML document coming in. Great. There's the head with a bunch of stuff. I don't really care for displaying this right now, but I'm going to parse it if there's any style sheets or JavaScripts. I'm going to download them and execute them as well. Then we have the body. Okay, that's actually interesting. The body is what I'm going to render later on. So I'm going to make a node. This is my body here. And I have a headline element, the H1, so the main headline. In there, we have an anchor. And in there, we have text. I left out the text bits, but basically, below here would be like text and stuff. Then we have a nav element somewhere here. And then there's links in there as well. And then we have text in there as well. Cool. So as we create this tree, which gives us a structured information of how the website's sort of going to look like and supposed to work like, we can start actually making certain arrangements. Because if you look at that, this is not really what you're seeing if you visit a website, right? That would be an interesting browsing experience, not necessarily the best browsing experience. Honestly, my Facebook feed would probably look better that way. Anyhow. So we take this tree as we are constructing it, and we can start figuring out how these things fit together. So we received a headline 1 element, so we're like, okay, so this is the main heading on the page. It's going to span the entire width of the window that we've got, and it's going to have a little bit of spacing here and there. CSS controls how that's looking like. So basically, when we get a CSS style sheet, we're doing the same tree building, but for the CSS properties, and then we combine the trees. That's happening as the document downloads. So we don't have to wait until everything has finished downloading, which is nice. So then we put in the header 1, and then we put in the anchor tag there, and then we can work out how large the text will be based on the font information and all that kind of stuff. Then we have a navigation. This navigation seems to be floated or positioned some way, maybe CSS grid, maybe flexbox, maybe floats, who knows. To the right-hand side, we're putting in the anchor tags there, so we figure out how large these elements are. So now we basically start composing the website. But these boxes still do not really look like the actual website. So after creating this tree, which is called parsing, and figuring out how large things are and where on the page they go, which is called layouting, we still haven't put any actual pixels on the screen for you to see. But we can do that in the next step. Because now that we know how large things are, and we have the style information like font size, font color, that kind of stuff, and position on the page, we can start actually painting. But what does paint actually mean? I mean, there's not Bob Ross coming out of my floppy drive and going, and here's a bit of, happy little cloud. That's not happening. So what does actually happen on the computer level? Well, let's have a look. So first things first, if we think about the screen, what it basically is a gigantic list of values, right? Each pixel is just like one value, a color value, really. It's like, okay, this pixel there is white, this pixel there is black, and there might be some other colored pixels in there, not on this slide, though. So we can basically just represent it as a list of things. Now, sure, yeah, it's a two-dimensional screen, blah, 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 but we could theoretically just like wrap around, like just add to the list, and then just, keep painting. But what does color then mean? Well, colors on most screens, except you're printing, then it's a different system, are expressed in 3 different color channels: red, green, and blue. There's a 4th one that is like hypothetic, which is the alpha channel, which means how transparent something is. But in the end, the screen is not transparent, so we can't make something transparent and then see what is behind the physical screen, unless it's like a really interesting display. But normal displays do not allow us to do that, so that's only used internally before we get the final color on the screen. So we have red, green, and blue. So we have 3 values. How bright is the red for this pixel? How bright is the green and the blue for this pixel? And these values are between 1 and 0, or 0 and 255, usually. Why 255? Well, 1 byte, conveniently 8-bit, contains 256 different values, which is 0 to 255. So that's where that comes from. And that's also why you have these hex codes. 1 byte conveniently can be expressed in 2 hex digits. So if you like FF, then what you mean in hexadecimal is 255, which means full on whatever channel you're having. So basically, we just have a bunch of numbers and a list. So we have a list of numbers. It's like this: I have a pineapple, I have a pen, pineapple pen. Who knows that video, by the way? It's great, isn't it? I love it. It's one of the better parts of the internet, really. So we have 3 numbers expressing each of these little dots here, and then just like lots of them representing the entire screen. So we have a list of numbers that represent the screen content. So when we say we paint, it's not Bob Ross senses of paint like going like, zack, and you're like, no! And then he just does something, and you're like, wow! Instead, we're just filling in numbers into lists, which for some people might be really exciting. It's not that exciting, but we can do cool stuff with it, as I'm going to show you later on. So the problem there is screens these days have quite a bunch of pixels. So if this is an HD screen, a full HD screen, we have 1,920 pixels in one line, and we have 1,080 lines. And we have to store 3 bytes per line. So if someone made like the math here, did the math for me, which I completely didn't, it is quite a bit of memory actually that we have to get over the network or over the cable to the screen. So it's basically 6.2 megabytes for 1 frame. So if you think about this, we have 60 frames per second is what we are targeting. That means we have approximately 10 milliseconds to to put in 6.2 million numbers. That's quite a bit, right? And if we do that 60 times within 10 milliseconds, 60 times a second, then that's quite a bunch of data. So if you think about like animations and stuff and like making something really graphically expensive on the web, think of throwing floppy disks at your users, because that's what you're kind of doing. Oopsa. All right, so now we need a way to make this efficient, because we don't want to throw floppy disks around, really. We'd rather do like a little more classy things. So this is where the compositor comes in. So just imagine you have like a JavaScript thing, and you want to move one thing around in front of another thing. In this case, we have a background, and we have a nyan cat. And what we want is the nyan, 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 and we don't know how to do that efficiently, and we don't really want to throw around floppy disks. So there's another component built in that makes life a little easier for us, and it's the compositor. So instead of having to like draw every pixel over and over and over again, what we do instead is we save one sprite or layer or image, which is the background, and we save the other one, which is the nyan cat. And then what we do is we go, okay, so let's fill the screen with a background. So now we have to actually like throw floppy disks at the user for 6.2 megabytes. And then we override only where the nyan cat goes. And for the next frame where the nyan cat moves a little bit, we only like rewrite the bit or re-put the numbers in again for the bit where the nyan cat was before, and then put the nyan cat at a new position. So we're only rewriting a small portion of that. We are no longer transferring 6.2 megabytes of data. We are only basically clipping the things in the different ways. And another way of explaining this, you could think of having a whiteboard. So we only draw the background once everywhere onto the entire whiteboard, and then we just go like, draw a little nyan cat here, and then take a picture, then just erase the nyan cat here, redraw the background here, erase the next bit and put it next to it. So it's very, very small operations there. And these copy operations, because that's what we're doing, we're overriding by copying numbers around, are relatively fast. What isn't fast is repainting the entire thing again. That's not going to be fast. So we are breaking things up into these layers or images or tiles or textures, depending on who you're asking. So how does that work? Well, technically speaking, if we have a bunch of images that we want to combine to a final image, there is the compositor, which is running a shader. And everyone who does not have the pleasure of having computer graphics in university or something goes, what? What is a shader? What does he say? What is a shader? So it sounds complicated, but it's actually not that complicated. So you might have heard the term GPU. So shaders are something that is optimized for the GPUs. It's basically a program that we can run. But the program runs on a different kind of processor. So the CPU is basically one big smart thing, a smart little emoji there going, hi, how are you doing today? Having a good time? Maybe your phone has like 4 or 8 of them. The GPU, on the other hand, are smaller blobs, smaller brains, smaller processors, but lots of them. So your phone might have 1,000 or 2,000 of these little cores in the GPU, but has only like 4 or 8 or maybe 16 of them for the CPU. But why would you do that? I mean, can't we just like get 1,000 of our CPU cores? Wouldn't that be like super cool? Can we then just not like do more things? Actually, no. And the reason for that is the same reason why dividing a task between 2 people and 20 people is not always as efficient, right? Just imagine if I say, okay, look, we have to like highlight the word YOLO in this printout from the internet. How about I give you 100 pages, and you take 100 pages, and I take these 100 pages, and then we just do it, and then we are done 3 times as fast. That's great, that makes sense. But have you ever tried to, like, let's say, bake something with 20 people at the same, like one thing with 20 people at the same time in a kitchen? That's really hard, right? So like, let me put the, no, go out of the way. I need to get the thing out of the oven. And then it's like burn, and everyone's crying, and it's a mess. And you order Pizza Hut, and you're just like sitting there sobbing into your pizza. The reason is that certain tasks have dependencies. You can't just break them down that easily. But when you can break them down, that's really, really cool, because you can distribute them to a large amount of, let's call them workers, or cores in this case, so little processes there, and let them calculate that. Let's have a look at that in practice. So here we have a little program, and basically is a loop that reads from a certain point of memory that depends on the position in the loop. And if the value there is 5, then it writes to a different memory location that also depends on the loop, the value of 5. So the question there is, what happens if I give this to like 10 different processes? They're going to be screwed. Because the first processor writes at the second memory location the value 5, but the second processor has already read that location. It was not a 5, so it doesn't do anything anymore, and the result is wrong. So normal program execution is not very good to make it in parallel. If you've ever worked with threads, you know that, because you had a problem, you tried to solve it with threads, and now you have problems too. Because things get out of order, and things get weird, and things might like clog each other, and then it's really, really sad. That's not a good story. However, there is a problem, a kind of problem, where these like parallel processors really, really shine. So if you had the pleasure of having to do matrix multiplication in school by hand, then you know that basically what you're doing here is, for each of the cells in blue, you just take a certain cell from the green, and you multiply it with a certain cell from the red, and then you put it in a certain position in the blue. And then you do that all over again. But it doesn't matter if this is that, then this, no, that doesn't happen. It's just like, and you just like do it all over again. The processor can do that. It's just like going to take ages, right? So the processor might start here, and then it reads this value, and then it puts it in here. And the other guys, like these wonderful 16 cores, they might just go, hey, you know what? I take this one, and you take this one, and so on and so forth, and we're just going to do this all in one go, well, 16 things at a time, because we have 16 cores here. Okay, now multiplying lists, or in this case, matrices, is a task that can be done in parallel. Now, what does that mean? Well, conveniently, our screen is a list, or a matrix, if you wish. How convenient that is. So now conveniently, which is not the reality, we have exactly 16 pixels and exactly 16 cores, which is very convenient. In reality, it's not quite as convenient, because we normally have much more pixels than we have cores. But still, each of these can do something with the pixels that we give them as inputs and produce an output that we put on screen in parallel, because there's no dependencies between them. So maybe we give them a function, like we say, look, I give you the x and y position. Let's say like this is 0x and 0y. This is 1x, like 1, 0, and this is 0, 1, and so on and so forth. So like the value of x increases in this direction, the value of y increases in this direction. So you please take the position that you're responsible for, which is x and y, and produce us 3 values. 3 values, that's strange, right? Red, green, and blue, that's why it's 3 values. You use x multiplied by 85 for the red value. You use y multiplied by 85 for the blue value, for the green value, and you use 0 as the blue value. And then what you do is, in one go, you get pixels on screen. That was easy. And guess what? That thing here, that's a shader. No magic. It's a function that takes inputs and produces outputs. Not that hard. Now, obviously, this shader is a bit pointless because it's just going to draw this kind of stuff on screen. It's more or less useless. But you can do other things in this kind of manner. If you want to move something around, you just have to offset where you start looking at things. So instead of looking at my position, I'm looking at someone else's position and then render. And if everyone does that, if everyone in parallel like moves one seat to the right, then everything moves to the right. So that's motion, that's translation, also called translation. So it's moving things around. If you want to rotate things, that's just a more complicated matrix transformation because you have to have a rotation matrix with the angles that you want to rotate around. But still, if everyone does it at the same moment, then it just rotates. It's not like there's no dependencies between them. So we can do that in the shaders. We can scale things. I just multiply. I just read the same value multiple times, or I skip values, and then I scale up or down. So we can do translate, rotate, scale, but we can also do things like opacity. Because what I can do is I can look at the fourth number, which is this alpha value, and say like, so I have red in one list, and I have green in the other list, but the red, I should only consider 50% of it. So you only basically, you multiply that value with 0.5 before, so you half it, and then you add that to the green that you already have. So you get this layover effect. So you can do transparency. That's nice. But there's a few things more that you can do, but unfortunately, not all the browsers do this in shaders. So there's a bunch of CSS features that also can be done in shaders that are not always working in shaders. So some browsers might repaint, and then it's going to get a little slower than you wish, maybe. So here we have an example. This is a really simple thing. It's a drawer menu. You can slide it in, and you can slide it out. And the cool thing is, in the developer tools for most browsers, you can turn on that it flashes a colorful rectangle on where it repaints. Remember, we don't want to repaint. Repaint is like erasing and then like re-putting it in. We don't want to do that. We want the shader to just go like, yeah, I have these pre-computed numbers. I'm just going to copy them over. Just copy them over. That's all I want to do. So when we see a flashing, colorful rectangle, that's a bad thing. So let's have a look. How often does this happen here? Maybe, I mean, this is just moving this thing in and out. So this is a translation, so this should be fine. We have learned that we can do this in a shader. Okay. Each colorful flash is a repaint. So that's quite, I don't know, I would call this a bit of a disco. So we got a repaint disco. It repainted a lot. That's not a good thing. Let's have a look at the timeline. So this is in the developer tools, we can see what the browser did. So I'm not exactly sure, this is like layouting, that happens every now and then, that's fine. The big green blocks here, that's painting. So it has spent a lot of time painting pixels again, which is something that we want to avoid, right? And here we also see like this is here we go. This is the frame rate. So we want to be like on the top of this, and sometimes we go down to like more or less half of it. So we sometimes have 30 frames instead of 60 frames per second, and that's on a MacBook. Imagine that on an old Android phone or an old Windows mobile phone. That's going to be really painful. And this kind of navigation is kind of made for mobile, so it's maybe not very good. So what can we do about that? So let's have a little quiz here. Put your hand up if you don't like to put your hand up for questions from the speaker. Excellent. So you're going to be asked a few questions. You can win nothing. But actually, you can probably, maybe I have a bit of Swiss chocolate with me. So if you want Swiss chocolate, make a positive. Yeah, not everyone, though. I'm not that rich yet. So if you make a positive impact and I point at you, then you get chocolate later on. All right, so let's have a look at this code. So here we have a CSS transform for the translate X. So we are translating it nowhere. And then what we do is, after a while, after 2 seconds, we are translating it on the x-axis to 200 pixels. Does that paint? Who thinks yes? Who thinks no? Who thinks I shouldn't be doing this? Tough luck. All right, so let's have a look. Again, remember, the developer tools will flash a rectangle when a paint has happened. In this case, it's a green rectangle because I'm using Chrome for this demo. So here's our little friend, and oh, let's see it again. Oh, the green rectangle of sadness. So that's not good. What happens here? Well, what happens here is not good because it pains, and that means that we're going to be slow, and we want to do it differently. And Martin, why did you lie to us? You said that translation can be done in a shader. Why would you do this? Well, because it's a little more complicated. So if I say shaders, like copy things over, what I actually do is I take these layers or textures or images. You remember like the Nyan cat and the background? In this case, it's like the background of the page and the smiley face. I put them into different images. That means that I put them into lists somewhere in the memory. So that means that for each pixel of these lists, I have to have some memory set aside. So if I have lots of them, let's say like I have a list with 500 elements on my website, and each of these elements is its own image, then we have a lot of memory just spent to like have a copy of each of these items in memory somewhere. That's going to spend a lot of memory for nothing, because I'm not going to move these lists individually. I may scroll, but that's still all right. I don't need to repaint them individually for this. So the browser tries to be clever about limiting the memory cost, because each of these layers costs us memory, so we don't want to have too much of them, so the browser tries to be smart about them, and what it does is it takes hints. So for video elements or canvas elements, we're going to repaint them often anyways, because it's like the content keeps changing, we can't really be smart about that much. So those are on their own layer. They are living somewhere in memory separately and then being composited in, so the shaders run them into the rest of the page. 3D transforms, because 3D transforms tend to be expensive because you have like perspective transformations and things like being farther away, being smaller and stuff like that. So like, okay, these 3D transformations might be tricky, so I'm just going to put them onto the shaders because they are better than the CPU in repainting things. Also transform-only keyframe animations. So an animation that uses CSS keyframes and does something that can be done entirely in shaders, like opacity, or moving things around, or rotating things, or scaling things. If it's in an animation, even if it's a two-dimensional transformation, it still goes into a layer and means that it's not repainted, it is being composited in. So that's pretty cool. So the browser takes these hints, and there's, oh, sorry, I skipped that one. There's one more that I forgot on this list, which is the new will change CSS property. It's a hint to the browser. The browser might put it on the fast path. Might. It's trying to be smart about that. OK, let's have a look again. So, slight change in code. Tiny little bit of change. After 2 seconds, we are changing the translation again. Will this paint? Who thinks yes? Who thinks no? Who can tell me why not? Everyone's like, whatever. I kind of said that, but people still think that it might repaint. But it's not going to repaint because it has 3D transformations. So like the translate 3D, even though it is still the same thing, makes a huge difference because it puts it onto the composited path rather than the other path. Yay! So that's pretty good. Any takers? Just shout yes or no. It's fine. No. No. Yes. Maybe. Who is that guy in the front of this room? So will it paint? No. Because again, it's kind of the same thing, but it's an animation. And even though this is a two-dimensional transformation here, it won't repaint because it goes, this is a keyframe thing, so it's going to run for a while, and it's probably going to have to be like moved quite often. So I can be smart about this and put this into the compositor. So that's quite nice. So we get smooth, silky, perceived things. And now I have bonus content. The thing is, I literally only found out basically this morning, so I couldn't really do much because I had another workshop to prepare for. So what I did instead is I'm combining with the previous talk I did. And this is my bonus content. Yay, surprise bonus content. Cool, so now we have seen how like the rendering works with DOM elements and stuff and how it works with CSS animations. But what about Canvas 2D and WebGL? Who here knows what Canvas 2D is? Who here has used it? That's fewer people, okay. Who here has seen how WebGL works or what it can do? Okay, so WebGL is usually perceived as a 3D graphics thing, whereas Canvas 2D is mostly perceived as a 2D graphics thing on the web. Okay, let's have a look. So I want to take an image on the canvas and in WebGL. I want to take the same image, just one image, and draw it multiple times at random positions and a random size, like blowing it up and making it smaller and whatever. And I want to measure how often I can do that, like as often as I can each second. So I want to see how the render performance does this. Let's have a look at the code first. So for the constant num images, let's say like 100, 200, 500, doesn't matter, I pick a random position anywhere on a full HD screen, and the random size factor between 1 and 512 times the size of it. No, actually, no, that's not true. I'm just using it for draw image. So basically, we're drawing this image around a certain position and then with a certain size. So this is like anything between 0 pixels and 512 pixels large. Okay, so that's all the code. That does exactly what I just said. Like it runs this loop and draws the 5,100 whatever images, and then I can measure what the frame rate will be, like how fast the computer actually can do this. For WebGL, yeah. And that's the cut-out version. Like that's not the entire thing. So we're missing like a bunch of stuff because I couldn't fit it on the slide. So this is the actual drawing, and this is the setup. And then there's like some more setup before that. So don't, it's a little more effort, I would say. NPM install sadness maybe. I don't know there's much of a thing that you can npm install out of your way. Maybe 3.js, but then you have like lots of overhead in 3.js. So it's like, yeah. Anyway, this is the rest of the setup code for WebGL, I think. No, this is still not the rest. So here we are setting up the vertices. Here we are setting up the texture coordinates. Put them into buffers for vertices and texture bits. Then we set the clear color. Yeah. And oh yeah, here we are compiling the shaders. So the shader sources are missing. So yeah, that's great. I would say Canvas wins for simplicity here. But let's go to the performance. So with Canvas 2D, if we draw one image, then we get a smashing 60 frames per second on a 2016 laptop from Lenovo. If we draw 100 images, we get around 30 frames per second-ish. And let's not talk about the rest of the numbers. Because really, if the green line is what you want to, like the top line is what you want to hit, the medium line is what you should at least hit. It's like 25 frames per second that make an animation look more or less smooth. And everything below like 10 frames per second is just, of like 12 frames per second is just a slideshow. So the performance doesn't look terribly great here, except when you only draw one image. That's amazing. Can we have a look at what WebGL does? Oh yeah, that's just sadness. Like no. So this is WebGL in comparison. With 1,000 images, it just goes like, what? You were saying, right? So that's the power of fully enabled shader pipelines. WebGL runs through the shader pipeline, the compositor, whereas the canvas still has to go through like serializing things from JavaScript into actual numbers and then passing that into the paint thing, and the paint thing might go like, I don't accelerate this. And even if you turn on hardware acceleration, I have a later slide, I think somewhere in the bonus material, where I turned on hardware acceleration for the canvas, where it tries to do as much shadering as possible. The shaders are still not smart enough to figure out what we are trying to do. So it's still slower because we have to go through the JavaScript model into like the actual shader pipeline. And whereas with WebGL, we have to code most of that ourselves, but we get full control of the shader pipeline. Oh yeah, here's the accelerated canvas. So with 1,000 images, with the Canvas 2D accelerated, we still get like 15 frames per second, whereas WebGL still goes like, whatever. Afterwards, it goes down, but it's still doing relatively well. And I mean, I didn't optimize the shader because that would be unfair. Okay. So, we have a draw. Let's have a look again. Let's find the edges in an image. What does that mean? Well, what we're doing is something that is a little nastier than what we did before, because it actually puts a bit of pressure on the shader pipeline as well. What you do is you basically look at multiple pixels. So let's say for this pixel, I look at the 8 pixels around it and have a look at the colors. And if they more or less match in a certain way, then I can assume that this is a, let's say like these colors, I have like my 9 pixels and half of them have one color and then one on or the other 3 on the other side have a different color. Then I can assume that this is probably an edge. The same goes for horizontal. And then you can mix that. There's something called the Laplace operator and the Sobel operator, and you can use these. Basically, it's just like how much do you value each of the pixels around the pixel you're looking at. Okay, so what we want to do is we want to take a picture and turn it into this. So wherever there is an edge, we want to put a white pixel in the output. Wherever there is not an edge, we just put a black pixel in the output, and then we get an image that looks like this. Now, this is more or less like most of the code that we have to do for the canvas 2D. The isEdge function is what I do, what I described, like we're looking at the pixels around the current position and find out if this is an edge or not. And if it is, we're going to put white. If it is not, then we're going to put black color in this particular position, and then we are copying the data back. So we click on the threshold because we can determine how much of an edge we have to have. So I click on something, like click, and 2 seconds later, it updates. By the way, the entire browser hangs. Like this is done in JavaScript, the entire browser completely freezes for 2 seconds, and that is on a 2017 MacBook. It's not particularly exciting, is it? So, yeah, we can have a look at the timeline. So I used the user resource timing APIs, and I basically colored in what edge detection is. So here we see like this is when edge detection happens, and we see like it just is, the red here is not a good thing. It means the browser has literally stopped responding to anything, right? So for 2 seconds, we're not really doing much, and it's entirely JavaScript work. Not. Well, the browser can do that because it only displays this one after it has finished this actual task. So let's have a look. This is like 2.6 seconds. So I was a little easy on them. It's actually 2.6 seconds. WebGL, on the other hand, we have more or less the same code. It's not that much difference. I mean, it's a little more because here we are putting like a white color in if the edge red, green, and blue divided by 3 is larger than the threshold. So we're basically averaging the color channels we got for the edginess for a certain pixel, and then we decide if we put in white or black. Okay, sweet. So it's not that much code compared to JavaScript either. It's like more or less the same. And the performance is slightly different. No red bar, no weirdness. It's 827 milliseconds. It's still not great, but at least we're relatively fast. And there's like no JavaScript executing. It's just like the entire execution happens down here, and that's on the compositor. So we don't have to deal with that. And we can click on things, and we can move things around on the page. So that's like, yay, the user can still interact with our stuff. That's great. So I would chalk down that's a win for WebGL because code is more or less the same, but performance is much better. I can actually see if I can find the demo real quick because we have a few more minutes. So I think it is, if only I could remember things, but I can't. Let's have a look. HyPerf.js demos. Okay, so it's like HyPerf.js demos, and I hope that I have an overview page. No, of course I don't have an overview page because that would be easy. Oh, it's also written differently. So no, it's actually not written differently. I did this right. So it's like 1-main thread. So let's have a look. /1-main, I guess like this, or is it? Well, I have a typo now, so that's not going to help. I think it's main thread in one word, right? Let's have a look. No? What? Or am I just not on the internet or something? Like, what's going on here? Can I click on things? Yes, I can click on things. I have written things and stuff. So this is downloading the image in the background now, I hope. Please tell me that you're doing that. Why is there like bazillion errors? Oh, that's not very good. Oh, there's this, god damn it. There's like a broken service worker from some experiments, and it's like screwing me over the entire time. That's not very nice. Not very nice. So the image is quite large. So I can now, you see this, like I click on this one, and then like the entire page does not do, oh, this is actually faster. Hey, look at that. No, it's like still like 2 seconds. 1, 2-ish. Still not very good. So that's what happens on the main thread. And I can click somewhere else. It just doesn't do it then. It just like completely blocks out until it has done its work. It's not very convenient. I can use web workers. So I can offload this to a separate thread, but it still has to use JavaScript. So I get these like, it still takes 2 seconds. It's just not blocking my UI, so I can now do like, yay, hi. So I fixed the blocking, but it still takes long. And then I can run the same thing with WebGL. And, right? I got a much more direct feedback. So I would say it's fair to say WebGL wins this one. I mean, I don't know, maybe you think differently, then again, I'm the one on stage, I have the microphone, so I'm right. So generally speaking, we can say like Canvas usually has easier code, oftentimes for many things. WebGL is a little trickier, but WebGL has like lots of libraries available. Canvas doesn't give you direct access to the shaders, and WebGL does, which is like nice. Canvas, even if it's accelerated, can only do so many things, especially because it doesn't have the possibility for you to reach directly into the shader pipeline. There's still conversions going on, and there's still like lots of work to do to like transfer the memory between the different things, like the compositor thread and the main thread. So there's like very limited performance. But that being said, depending on the device you've got, you get varying amounts of results from WebGL as well, right? If it's a really, really low-end device, you might not have a good time with WebGL either. So do you WebGL all the things because it's so much faster? No. Please don't, because you lose a lot of things. You lose the semantics. So if you have semantic content, use HTML and CSS, because these are like searchable, findable, they are assistive, so like the assistive readers and the browser can help you a lot. A button just works like a button. If you do that in WebGL, you have to re-implement it. A few people have tried, none of it has caught on, there's a reason for it. It's not that nice. Also, you get like all these UI primitives, you get things like sliders and input fields, you have to reinvent everything if you use WebGL for it. SVG is great if you want to do like image content or animations that have to scale nicely. So if you need like shapes or animations or whatever, what have you not, diagrams that are really responsive to the size of the device and can adapt to the content that they are embedded within, then SVG is the right tool for this. Canvas 2D is great if you have like simple 2D shapes and very simple two-dimensional graphics operations that are not taking a long time. But things like edge detection or computer vision, Canvas 2D is just not cut out for it because you are limited to the CPU, you don't get the parallel processing power from the GPU there. But that's where WebGL shines. And it also is useful for two-dimensional graphics. The edge detection is not 3D graphics, that is 2D graphics. So if you were to build Photoshop but in the browser, WebGL is a good candidate for that. And with that, oh, that's the other slide deck. So let's move back to the original slide deck. And with that, I want you to build cool stuff that performs well and makes your users happy rather than slaggy, terrible, sluggish, long, short thing. This does not, don't do shit. That's basically it. Right? Thank you very much. Have a great day.